very much. So I'll be talking about ICT for sustainability, but more particularly we'll be looking at combinatorial optimization. So this is our main field in Cork. I'll give a brief introduction to what this is, discuss some general sustainability applications of this technology, and then we'll move into the main focus of the talk, which is about energy-related combinatorial optimization. So looking at forecasting of real-time electricity price for the Irish market. We're looking at energy management systems. We're looking at train timetabling, energy efficiency for train timetabling in electric rail networks, and also energy efficiency for data centers. So combinatorial optimization is a problem, not to get too mathsy on you, but a problem of the form where you've a set of variables, and each variable has to be assigned a value, and you've got constraints which restrict what values variables can take. And then you've got some objective function that has to be minimized or maximized. Just a simple example, we have a knapsack problem. So we've got a knapsack of fixed capacity, and you want to work out how many of each item to put in so that you maximize the value while still respecting the capacity of the knapsack. So this has many applications in sustainability. Regina mentioned earlier the carpooling. So one thing we look at is optimized carpooling, optimized ride sharing. This is with a San Francisco-based company. So we want to maximize the number of passengers covered by all the drivers while still respecting car capacity constraints and location and temporal constraints. So if you've got a passenger that's earliest leaving time from location A is at 9:30 and the driver's latest leaving time from location A is 9, then this passenger can't go with that driver. So we model these problems with using mathematical modeling techniques, and we solve them then for optimality. So in this problem we were able to show that through the modeling that flexible participation, where we asked drivers to also be allowed to go as passengers, could reduce unmatched participants by up to 80%. Another application was in the area of forestry. It's with a company in Cork called Tree Metrics. So you've got forest owners with several forests, and they have customers that have specific demands, and we want to minimize the cost and conserve natural resources while still satisfying the demand. So if we optimize cutting approaches using the combinatorial optimization techniques, we're able to satisfy the same demand with requiring fewer trees. So as I said earlier, the main focus of this talk is going to be on energy. So we're looking at a few different applications. We're looking in the residential sector, we're looking in the information technology sector, the transport sector. I'll be discussing all three of those. I'll also just mention here another project in natural resources. I won't be discussing much further, but just to make you aware, so we're looking at minimizing the energy cost of underground mine operations. This is with a company Bolide and Tara Mines and DCU. So this is minimizing the energy cost for a zinc mine in Tara Mines. So the motivation for this work, well, on the demand side, there's quite a significant increase in energy demand. For example, in data centers, it's accounted for, I think, roughly 2% of the worldwide consumption is coming from data centers. This consumption with data centers is obviously growing annually. Similarly, in the residential sector, it typically accounts for about 30% of national usage. And with the predicted increase in electric vehicles, this is obviously going to increase the consumption in the residential sector also. On the supply side, the significant changes is the increase in renewable energy. So what does this mean? Well, the drawback with renewable energy is that you can't schedule when the wind will shine or the sun will blow. So it's intermittent. So it means what we're doing is we're moving from the old system where we're trying to match the supply to predicted demand to a new system where we're trying to match demand to predicted supply. So to match demand, we need to incentivize the user, so to shift their loads. So utilities can do this through pricing strategies. So I'll be focusing on real-time pricing. This is where the user pays the actual cost of the energy they the actual cost of the energy they consumed. So the energy cost of our scheduling, what we want to do is we have a set of energy consumers, and we need to schedule these over fixed horizons. So say for the next 24 hours, we need to schedule the following 20 items. So we need to know what's the optimal time to schedule these items such that we minimize total cost. Now with real-time pricing, we obviously don't know the price in advance, so this requires price forecasting. So what we do then is you schedule based on the forecast, but you will pay based on the real. So that means that the forecast is quite important. So UCC developed some forecasting. We compare this with a forecast given by the single energy market operator in Ireland. So we're able to outperform it. But an interesting thing we found is that the forecast that had the best, that was best according to the traditional metrics of mean squared error, didn't produce the best schedules. And this is because the actual ranking of the time periods is important here. So if you have the dearest time period and you predict that this is going to cost €10 and it really costs $9.99, that's great, but from the schedule's perspective, it wouldn't make any difference if you said it was going to cost €1 million per kilowatt hour. You would still try and minimize how much you put into the dearest time period and maximize how much you put into the cheapest time periods. So actually getting the ranking right turned out to result in better forecasts with improved schedules. So one problem with real-time pricing is that the user is often unable to react to price changes. So say a person in the home, they see that at 4 o'clock tonight the price will be really low, but they're not going to set their alarm to get out of bed at 4 in the morning and turn on the heating. So what we need to do is we need to give them a home energy management system. So this automates the usage of flexible energy consumers like heating and cooling, like electric vehicle charging, like washing machine, different appliances. So we want to optimize the scheduling while still maximizing user comfort. This was joint work with Intel Labs Europe. So here's a home energy management system. It takes input from the user about their temperature preferences, about what battery charge the electric vehicle needs to be at every morning, etc. It takes inputs about the electricity price over the next 24 hours, and it takes inputs about the weather so that it can work out the thermal model for the home, how much heating is required. And then it produces the optimal charge discharge for each time interval. It produces the optimal temperature set points, etc. So experimenting with Irish data, we were able to achieve average daily savings of approximately 20% by optimizing with this. So just to give you an example, and this may seem slightly counterintuitive, so the optimized uses the minimum energy to meet the user's goals. The non-optimized actually use more energy, but it uses more energy at much cheaper time periods. So it actually preheats the home to a higher level and then allows the temperature to fall off back to the user's required preference. So this produces savings, and this also means that you're using, if the energy is cheaper, a lot of the time it's because it's more renewable, it's more environmentally friendly, you're not having to use the more expensive energy generators. Another example is energy efficient train timetabling. So you've got an electric urban light rail network, so this is the London Underground. And in this you've got spikes in consumption when trains accelerate, and then negative peaks. So most modern electric rail sector, they have regenerative braking, so this recoups energy when braking. So here's an example of a power profile for a train from its start station to its end station. So each peak corresponds to a train leaving a station, then you've got a flat part where the train is at its operational speed, and then you've got a negative peak where the train is braking as it enters the station. So you've got all these different trains going at all these different times, so what you want to do is you want to stop any huge spikes. So you want to balance the trains arriving at stations with trains departing stations. So we need to assign departure times for each leg of every train, and you're subject to constraints on safety and train connection times, etc. And you want to minimize the peak consumption over each 50-minute time period, because peak consumption causes stresses for the utility company. So they actually charge an additional flat fee for each peak consumption, or for the peak consumption over their time period. And we were able to produce an average reduction in peak energy of 24%. So just to give you an example, the black triangle is the initial schedule, and the green squares are optimized version. And as you can see, the peak was over 20 megawatts with the initial schedule, and we're able to flatten this down to 15 megawatts peak consumption through this optimization approach. Final example I'll talk about is data center energy reduction. So this is part of a European project, GENIC. And combinatorial optimization is used for reducing the energy consumption. So energy consumption in data center comes from computing power and cooling power. So we've implemented a thermally aware, energy aware server consolidation. So if we optimize this with workload prediction, this gave an expected reduction in energy consumption in a single data center of approximately 40%. It is a significant amount. However, we can also take advantage of the fact that there's data centers all over the world. So maybe instead of having the load, optimizing the load in one data center, we can take all data centers. And we can take advantage of the fact that these data centers have varying climates, they have varying price tariffs, and they have varying DC energy performances. So in January, it might be better to move the load to one location, or at night time to move the load to one location. So even just to give an example, this is average temperature in each of different locations for each month of the year. So as you can see, by shifting the load between different data centers, you can make considerable savings. So again, with some simulation-based experiments involving 21 data centers around the world, you're able to produce energy cost savings of between 20 and 40%, depending on the percentage load in data centers. So basically, I hope I've given you the idea of the breadth of combinatorial optimization and the uses of it. It's many applications in sustainability and outside of sustainability in health and transport, etc. So what it can be used for is improving efficiency, reducing waste, and reducing cost. Thank you.